audio, record, share, window. Okay, good. So far we've focused on creating models in R, code in R that can generate data, can play the game according to our models of the mechanisms that might generate human behavior. And what we're going to focus on today, next time, and in the next few weeks is how do we go instead from existing data to inferring, if we know the model already, which parameter values have generated these data. Let's say if we assume that people are playing like a bias random agent, what's their bias? If we assume they're playing as what they're called as a reinforcement learning agent, then their learning rate and their temperature. If we assume memory model, right? What's the weight that they give to memory, and so on and so forth. And in a second instance, we will learn if we don't know which of these models might be generating the data, how do we ask the data which of these models is most likely? Right. So far, we have described the conceptual framework of cognitive modeling. We have formalized models of agents playing matching pennies as mechanisms that are not directly observable, but might generate the agent's behaviors. And by formalizing these models, we were forced to think more precisely, right? Making decisions about how do we think that memory works, right? How can we model that? How can we specify the mathematical shape of, let's say, older trials counting for less than newer trials? And we have simulated the behaviors generated by our models, right? And sometimes the implications are not always obvious. So by simulating data, we can actually explore what the model would do in different conditions. But also we have data in which we know the model that generates them, the true model that has generated the data, and the parameter values of that model so that we can actually test, once we get to build an inferential model, whether we can reconstruct the true model and the true parameter values. The next steps are, first, do you have questions so far? Has it all been super clear? Are you struggling with the assignment? Good. Have you been using the course notes? Are they useful? Should they be improved in some ways? Well, there's a lot of things that I want to do with them, but I want to hear. So far, they work. You let me know when they're not clear or difficult or confusing. Good. Yes. Mm-hmm. Yes. I think that's a good idea, right? So we do that in class, in lectures, but it's not in the course notes. Would you mind sending me a note or putting it in the Google Doc so I don't forget? Yes, because that's a good point to add. Good. Then I just want to wrap up what we're discussing on reinforcement learning. I'll be a bit fast, but we'll take up reinforcement learning again at a later stage. And then we will move from data generating to data inferred model, right? From models that we define and then we use to generate data to model that we still have to define, but that we try to specify in their parameter value or in which ones is most likely from the data. And I will be presenting how to code instead. But there is also a reference reading for today's or for this week in the
on Brightspace that you should check, because during a lecture we can only discuss the programming language so much. So just go and have a look, because it go much more in depth on that. Okay, so reinforcement learning. We discussed it a bit, which is a theory called in the original paper, a theory of Pavlovian conditions, which is a theory, a very simplified theories of how organisms learn to attribute values to alternative choices, alternative behaviors. Right? In the case of the matching penny, we easy life because it's a binary choice, right or left. And the reinforcement learning algorithm is a model that, based on its interactions with the word and the feedback that it gets, it creates internal representations of what's the expected value of picking right and what's the expected value of picking left. And this model is very popular in industry these days. It's used a lot, for instance, for ChatGPT, to train ChatGPT to produce better answers. So a lot of the basic uh, architecture of these large language models is, of course, learn to predict the next word, but that wouldn't make it a good conversational agent, right? So what these big tech consortia have been doing is they took a bunch of very lowly paid workers in Nigeria, in Kenya, and a few other people. And they had the LLM produce 3 possible answers. And then the worker would indicate the ones that's closest to a good answer. And the model is much more complex than the kind of reinforcement learning we do here, but basically that fine-tuned the large language model to actually produce answers to questions instead of just completing and keeping on, right? And it's a model that's very popular because it triangulates between behavioral data. It describes human and animal behavior in a lot of contexts pretty well, but also with neural aspects, neural data. For instance, what we see is that it's the mismatch, the difference between the feedback that the animal gets and the expectation of feedback that the animal had that corresponds to the activity of the dopamine receptors. And yes, a general, very algorithmic level description of the algorithm is that you have an agent which interacts with an uncertain external world, mostly in papers, in cognitive neuroscience, in decision making. It's an experimental setting, right, where we have a certain amount of possible choices. They often try the one-arm bandits, right? You have 2 different slot machines, 3 different slot machines that you can pick. Each of them gives a prize at a different rate. Sometimes the prize they give it even has different values. And by trying a bit, you need to form expectations of the value, the average value of pulling the one versus the other, and therefore optimize your rewards by picking the best. Right? But sometimes the environment is uncertain. Sometimes the slot machines are changing over time. And therefore, you want to keep learning and exploring every now and then. So in interacting with this uncertain external world, the agent uses the feedback from the environment, for instance, the monetary reward or the kick of joy that you get from beating your partner at the matching pennies game, and uses that to form internal values, right? The expected reward of the action if you take it again in the future. And it does so according to a specific learning rate, meaning you might be more or less dependent on the very last trial. Yes, I think, and this is called reinforcement learning because learning, well, the value is learned and not assumed. And reinforced, it's because positive feedback strengthens the association, while negative feedback weakens the association, the expectations, right? Weakens the association between picking that action and expecting a reward. We've seen these two parameters, the learning rate, which belongs to the estimation of expected value, right? The learning rate moderates the impact of predictive errors on the change in expected value. Higher learning rate correspond to faster learning, but also less memory. Right? We can say that if we expect an environment that's very stable, we shouldn't be swayed by, if we're good friends with somebody and we have a lot of fun and we can rely on that person, and on one day that person is very grumpy, right? We're not going to change the opinion of that person that much. But if it's a stranger, right, we might change it a lot. Or if it's a person who's very unreliable, we might be changing things more. If we have lower learning rate, we learn slower, but we keep the memory alive, right? The second parameter is related not to the estimation, but to the decision, to the implementation of the decision, right? We have an expected value of picking right versus left, but how determined we are by the difference in expected value depends on the temperature. The higher the temperature, the less determined we are, meaning we keep exploring. In the parlance of the previous models that we built, right, we could say that's a high noise in the decision. In the traditional explore, exploit literature, we can say that we keep exploring because we don't know whether we found the right expected values, or because we know that the environment changes, so we need to keep trying to estimate. If the temperature is low, then we are more deterministically affected. Now, there's here a little trick that's in reinforcement learning. We use inverse temperature, and I should have written that, meaning that high tau, high inverse temperature, means low temperature, no exploration. Low tau means high temperature, more exploration. And I hate that they invert the thing, but yes, that's how it is. I made a little plot on how different learning rates affect the impact of past trials according to how far in the past they are, where a high learning rate, 0.9, has basically only the last 3 trials mattering, while as we lower the learning rate, there is a low but still non-trivial impact of past trials. And how can we see that more analytically? Well, if we have, this is the value update rule from reinforcement learning. The value at time t is given by the value of that choice of the previous time, plus the predictive error that we get, moderated by the learning rate, right? Are there questions about the value update formula? Right, it says, take your value, change it according to whether you expected a higher value. So whether you got a higher reward than expected or a lower reward than expected. And how much you should follow this difference from your expectation depends on the alpha. The alpha only goes from 0 to 1, right? So it dampens the learning. It makes the predictive error matters a bit less than if we were to take it at face value. So if we imagine a series of outcomes, so as 1, 0, 0, 0, for simplicity, right? We have the first one where 1 is coming out, and the others are just 0, so we can observe how much that 1 matters over time. And we say that at time 0, we have a 0 expected value of picking 1, right? So we can see the jump immediately. We can solve the equation and say t equal 1. Well, the value at times 1 is equal to the value at time 0, which is 0, plus, oh, sorry, the outcome is the feedback. I made a mistake, right? The plus alpha times 1, the feedback, minus the value, 0. Right? So 0, 1, 0 plus 1 times alpha, which is equal alpha. Right? So now we have what the value at time 1 is, alpha. Then we take the value at time 2 is given by alpha, the value at time 1, plus alpha times the feedback, which now is 0, minus the expected value, which was alpha. Right? Which is, if we solve it, alpha minus alpha times 2, which is times 2, but it's alpha squared, which is alpha times 1 minus alpha. Right? We repeat it at times 3 and at times 4. And what we start to notice is that at all these steps, we have alpha times 1 minus alpha to the power of how many steps of distance we are. Right? Power of 1, power of 2, power of 3. Which is exactly why we're getting this exponential decay. Because by multiplying at every step for a number that's between 0 and 1, we keep discounting it more and more. Right? Yes. This is not temperature, this is time, right? It's how much in this sequence of trials that the model is playing, at which step are we? Yes. It means the expected value of picking 1 at time 4. So imagine it's like when you have interests rates on your bank account, right? You have by multiplying it by the same interest over repeated times, right? Your amount increases exponentially, right? So you're multiplying it by 101%, right? If you have a 1% interest rate. Here we're multiplying it by something that's a bit lower than 100%, right? If the learning rate is 0.9, it's by 90%. So it decreases. And then we multiply that by 0.9 again, right? So it decreases even more. And that's where we get these exponential effects from that formula. Do you need these for your model? No. But it's a way of trying to connect the mathematical formulation of the model to your understanding of the exponential decay in the impact of previous trials. Does it make sense? Is it too much at 12? Cool. So now we want to simulate data, right? So we have a value update formula, which I showed the other time. I'm not going to go too much through that. I'm just going to remind you predictive error is feedback minus expected value. V1 is the value of choosing 0. V2 is the value of choosing 1, if we're modeling things in a binomial. And these 1 minus choice and choice are just ways of making the value of 0 update only when the choice is 0, and the value of 1 only update when the choice is 1. We spit out V1 and V2, right? And that's simply the function on how to update value according to the function we've seen. Then once we have that updated value, and there was something that I discussed with Lauritz and I wasn't remembering the details, we use a softmax, which turns the difference between values into the probability of picking 1. That is the difference between the expected value of 1 and the expected value of 0. When we fit it here, it transforms it in a probability of picking 1. And it's just a sigmoid function, right? Are you all familiar with that, right? It's basically, as we're saying, the higher the tau, since it's the inverse temperature, the more deterministic the model is, the less there's noise in the system. That's why it's called temperature, right? Because when you have a solid or a gas or a liquid with a lot of heat, a lot of temperature, the molecules keep bumping into each other and creating a lot of stochastic behavior. When you have a low tau, that means that you have a lot of noise. And so here, imagine that the algorithm always chooses 1. Red is the feedback, right? It gets a feedback of 1, then it gets a feedback of, in this case, -1. You got it wrong. Again, and then again, 1, 1, 1, and then -1, and then 1, 1. And then we can see how the expected value of picking 1 changes. We can see that initially it's somewhere, it should have been at 0, I guess. I might have coded that wrong, but we get a feedback of 1. And our expected value goes pretty high. Right? We get another feedback of 1. Picking 1 is good. Then our expected value goes all the way up. Right? We have a very high expectation that picking 1 we win. But at that point, the feedback goes negative. It says, the penny was in the other hand. So our expected value for 1 goes down. We get another wrong, you shouldn't have picked 1. And it goes almost all the way down, right? So it's following the feedback in this case, right? And it has a high learning rate, meaning that it goes pretty far down, but not all the way. It takes a few trials to get all the way down. So now that you can read that plot, what we can do is we can explore different values of learning rate and different values of temperature to see how things work. So here we're just manipulating alpha, the learning rate, and you can see that as we decrease the learning rate from 0.9 in purple to 0.5 in blue to 0.2 in green, right? The adjustments of the expected values that the algorithm does are much slower. And you can see that it takes a long time to get to maximum expected value or minimum expected value. Does this make sense? It gives you a good conceptual grasp of the algorithm? Good. So then we can make it play against a biased random agent that plays once 0.75% of the time, so it's quite clear. And we can try different values of learning rate and temperature to see how well the reinforcement learning algorithm performs. Because that, at least to me, gives a much better understanding of how the algorithm works. What are the implications of the algorithm? And so here we have the different color in the single panel are the learning rates on the left, and the different panels are the tau. And we can see that the lower the tau, so the top left panel, that means the higher the temperature, the more stochastic the system, the more everything is a mess, right? It's really hard to pick a pattern at which learning rate is better because it's just exploring all the time. As we go to high taus, that is low temperature, less noise, we can see that it stratifies much more nicely. It's much easier to see a systematic difference in performance by the learning rate. We can see that the lower the learning rate is, the higher the performance is, and that the performance stabilizes at about, if you think, 3/4 of the possible performance, right? Which correspond to the 0.75 bias. Why is this? Why low learning rate is a good thing? Yes? Because, yes, rephrasing it, because the agent we're playing against has a stable latent state, right? More likely to pick 1 than 0. And deviations, apparent deviations on the short term, are just due to noise, to the stochastic nature of the agent. So we don't want to learn from the noise. We want to slowly hone into the latent bias. Which doesn't change in this case. If it were changing over time, then it would be a different thing, right? On the right is exactly the same data, but represented flipping which parameter is in the panels and which parameter is the colors, right? Where we can see that with high learning rate, independently of the noise, they kind of converge very quickly on, not very quickly, but after 40 trials towards the 0.75, right? Which on this scale is 0.5 because I'm stupid and I did it from -1 to 1. Sorry. If we have a low learning rate, we can see that it's actually only a high inverse temperature that is a deterministic system that hones there. If you get noise in the system, it's not getting there. So for instance, you could infer that having a high temperature when the underlying parameter that you're trying to approximate is stable is a bad idea, right? Which is what we discussed before, but now we can see it more clearly. And if there is noise in the system, a high learning rate is also a bad idea. Right? We start, at least from these plots, I start getting a much better understanding of what's going on. And as we go to more complex situations, changing biases in the agents that play with more complex strategies, right? We build bases for a much better understanding by plotting these sort of things. Good. Now we get into simulating, or not simulating, but building the inferential models from models that can generate the data. So I'm going to pick 3 examples that we're going to go through this week and next week. The random bias or biased random agent, where it has 1 parameter. That's rate or theta or bias, exactly the same. And it's embodied by the fact that the choice is given by randomly sampling a binomial distribution one time for one trial at a time according to the rate that we have, right? By the way, actually, that model generating the data, we could reconstruct that parameter using the GLM. We could use, a regression model to actually perfectly reproduce and infer data from that model. Reproduce data from that model and infer parameter values from that model. Any ideas? Right, basically, what we have is a sequence of zeros and ones, and that is a binary outcome, which is determined by an intercept. So here we have a logistic regression, right? Where we have that there is a specific beta which generates according to the logistic, so the binomial distribution, right? An outcome. So if I want to know the underlying rate in a sequence of 0 and 1s, I can simply run a logistic regression just with the intercept. And the intercept will give me the average rate underlying the 0 and 1s. Does it make sense? Right, think about when you make a model of performance in an experiment. Performance is success or failure, 0 and 1. You build a logistic regression, and then usually what you say is that you have 1 plus condition, right? In this case, we don't have any two conditions where we're trying to estimate two different rates. We're just trying to estimate the underlying rate. I'm trying to make connections, right? We have a second model, which is the noisy bias random agent, which is exactly like the one before, but it adds a layer of additional noise. These cannot really be reproduced with the standard GLM, so I'm not even going to do that. We have then the third, that's the probabilistic win-stay-lose shift, which I'm going to cover some pieces in the lectures. So here, I would say we have two parameters that we need to generate the data and to infer from the data, which are the probability of staying when winning and the probability of leaving when losing, right? If you wanted to transform this into a GLM, right, just because I want you to learn to think across ways of modeling things, how would you go at modeling it, right? We have the same binomial choice. What are the predictors of that binary choice? Yes? Yes? Okay, yes. So we could change this into win or stay, right? And then say that we have a beta for win, let's call it beta W, plus a beta for losing, right? And this is 0 if we lose and 1 if we win, because in that sense, if we lose, this beta doesn't apply. And here it's the opposite, right? It's 1 if we lose and 0 if we win. Does that make sense? However, these introduce a layer of complexity, right? We are recoding the outcome. What if we want to take the outcome as right versus left? Yes? Mm-hmm. Yes. So what we're going to have, what I would do is I would say that this one is -1 if we won and picked right left. So it pushes our decision towards left. 1 if we won and we picked right. And 0 if we lost. And here we would have that we have -1 if we lost and we picked right. So it moves away from what we chose. 1 if we picked left and we lost, and 0 if we won. Right? And if we do that transformation, then this is nothing else but a logistic regression. Right? Which sometimes is nice if you want to run something quick in BRMS, right? Or LME4. If you code these like that in BRMS, you also get a third parameter automatically, right? Which is the intercept. What would the intercept represent in these model? Yes? Yes. It would say, let's say that I'm right-handed, and I tend to pick the right hand a bit more than what the win, stay, and lose shift model would say. That's what it would represent. These kind of parameter is actually super useful when we model data from non-human apes, because their handedness is a really strong determinant of the behavior, right? And we want to account for that handedness in the model. Does that make sense? The last model is the reinforcement learning that we can see briefly. Again, it has 2 parameters, the learning rate, the inverse temperature, and cannot be reduced to the GLM. Okay, so let's say that we have defined these 3 models and we find them plausible and interesting, which doesn't need to be. You might find them as boring as hell, but they're pedagogically simple. So we start there. We need to check them against data. How good are they at describing real data? So first, we want to look at internal validity. That is, we want to know whether they can be actually fit to data that we know follow that model. If there are parameters, let's say bias, rate, theta, can the true parameter values be reconstructed, right? So if we fit the model to the data, do we actually get the actual value that we put in? This is called parameter recovery. If we have multiple models at stake. In this case, we have 4 I put there, and we don't know which is the right one. When we simulate data, right, we might simulate data from each of the models, so we know the ground truth, and then we can do model comparison on each of these data sets and see whether we pick the right model. And we call this model recovery. Then we have external validity. That is, now it works on simulated data in theory, right? How does it work on real data where we don't know what the true model is? We don't know what the true parameters are, right? There might be other models that are generating these data that we haven't. Actually, for sure, we will never have the exact true model, right? So how do the model predictions match the empirical data, right? Training, for instance, in the same data that we use to train the model, but it could also be testing. That is, we keep a few participants out. But it could also be external validation, right? So let's say that I have you playing the matching pennies here, but you're a very specific population, right? What if I went to my kids' primary school and have them play, right? What if I went to Quartzmoor and got people, engaged in a very exciting tournament of matching pennies, right? How well are these models as a general model of the data generating mechanism? In machine learning, this is what is usually called the distribution shift problem, right? So if you train your fancy machine learning algorithms on the data from hospital X, right? How well would it generalize to data from 6 months in the future or as hospital Y? Because there are important differences that will emerge in the distribution of the data. And knowing where your models fail is super important. We can also see how well the models compare on the empirical data. That is, of course, we don't know whether we have the true model amongst the ones we have, but we try to do our best to identify plausible models. Which of these models is most evidenced by the data? Or by a subset of the population, because different populations could use different mechanisms. I'll just do this before we take the break, which is as we try to set up these workflow, right? We need to specify the model. And to specify the model, because we're Bayesians in this class at least, we have to specify a likelihood and the parameters. That is, what's the equation that generates the data? And then we need to specify priors on the parameter values. Let's say we have a biased agent, right? What are the plausible values a priori before seeing the data for these bias rate theta thing, right? Or for the probability of staying when winning. Then we assess the model predictions before even seeing the data, right? We see, given the priors that we have and the formal equation of the model, what would we expect to see? Like if you went through methods 4, right, the statistical rethinking course, that was a very key topic from the second edition onward, right? These are called the prior predictive checks, which are often used to reshape the model, right? We might change our priors because, especially in a model like reinforcement learning, before starting to work seriously with reinforcement learning algorithms, I had no idea what plausible prior values for tau would be. I can get some ideas from those plots I showed you before, right? Which are plausible behaviors that we get at different levels of tau. But again, right, let's try different prior predictive checks, different forward simulations, and see whether we create something that's really implausible so we can restrict the possible values. We then define parameter values for the simulations, what makes sense to assess, generate data, and fit the model. Then we assess the model quality, right? We do prior posterior updates. So we plot the prior for learning rate and the posterior for learning rate overlaid to each other, and we see whether the model has learned from the data. Sometimes our priors are too specific, the model doesn't learn. Sometimes we see that the posterior is really at the boundary of the prior, meaning that the prior is constraining the inference. Sometimes that's a good thing, sometimes that's a bad thing. We need to be aware of that, right? Sometimes we see that our priors, go from 0 to 1,000, and our posterior is between 0.2 and 0.3, and we need to evaluate whether going up to 1,000 is an efficient way of using the computation power of our computers, right? We want posterior predictive checks, which is we have the posterior parameter values. We, again, generate data from these models, and we see how well they match the data on which we fitted the model to see whether the model is biased, right? Is systematically under predicting low values or high values and over predicting low values, for instance. And then we can check the parameter recovery. Did we actually found the true parameter values? And then we fit the model to real data. And then we again assess the model quality, right? Prior, posterior update, posterior predictive checks, and perhaps generalizability if we're interested in that kind of question. Then we'll do a lecture on multi-level modeling, where you code it from scratch so you actually learn what the computer is doing, and model comparison and model recovery, but that's for future lectures. And with that, we'll take a break. 10 minutes, so I'll see you at 15 over. Okay, so I had some good questions during the break, so I'm just going to go through a couple of points again to make them extra clear. So we can see here that we have prior predictive checks, posterior predictive checks, posterior predictive checks again. And that might be a bit confusing. Basically, everything that's above fit the model to the real data is work that we're doing without even opening the real data, right? We're just working on simulated data to see whether in principle our model can work. And even in the most conservative mindset, there we can do all the changes we want to the model without falling into questionable research practices, right? Because we're just trying to ensure that in this very clean universe of data that we know how they're generated, we know the level of noise, we know the parameter values, etc., the model gives us the right answer. The model works as it promises, right? Even regressions models will give you funny surprises when you do that. The prior predictive check is, right, just from the prior what the model expects to see. The posterior predictive checks, still in this area, it says, given the prior and the simulated data, what does the model think they're seeing? And sometimes there's a mismatch between the simulated data and the predictions of the model. Let's say that we put a prior that is very close to 0 in the learning rate, right? And the true parameter value is 0.7, right? The model will expect, even after seeing the data, behaviors that updates much more slowly, right, than the real data. And we would see that in the predictions. Then when we look at the real data, right, we have again a new posterior predictive check, right, where it's compared to the real data after it has seen the real data, because the real data is more messy and interesting than the simulated data, right? Now, some people would say, that's it, right? Your model sucks. Your model sucks. I'm a Bayesian. I don't care about that. And I say, well, wouldn't it be a good idea to make my model suck less? I'm not looking at an hypothesis testing, right? I don't care at this stage yet whether people with depression have a learning rate that's higher than people without depression, right? What I care is that my model can actually describe the data that we have within reason, right? That it doesn't just predict left, 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 right? And so I feel entitled to be transparent and go back and change the model again, right? Because it doesn't reflect the structure in the data. This was one discussion. Was there a question there? Yes. Oh yeah. So let's take the I don't know, the random biased model, right? So we have simply that we have a binary choice, which is a function of a rate or a theta or a bias. We say, right, what should we put as a prior for theta, right? We say, well, it should be 0.5, right? That's the center. That's just total chance. And then, well, we want to be very broad, right? We don't really know what the whole range is going to be, so we can put, say, I'm doing some errors, but let's doing them for pedagogical reasons, right? Then I'm going to say, well, let's give it like a standard deviation of 0.3, right? Which means that roughly now we cover something like 0.5 plus or minus 3 times 0.3, right? Which means that we go to minus 0.9, so minus 0.4 to 3 times 3, it's 0.9, 0.14, right? No, not 0.14, 1.4, right? And then we say, oh, that doesn't look right. So we're just going to say that all the values below 0 and all the values above 1 get approximated to 0 and 1. And suddenly what we have is that this is our probability distribution for the learning rate, where the most probable values are 0 and 1s. And that's like we can discuss it, but generally I would think it's a bad idea, right? We actually want the full range to be probable, not the extreme values. Right? And that's before seeing the data. Now you could say this is silly, right? Nobody would do this. Nobody would model the rate as a normal distribution. Well, talk to the economist. It's called the linear probabilistic model. They do that all the time. But we're smarter, right? We talked about logistic. So we are working on a minus infinite to plus infinite log odds scale, right? So there we can put a normal distribution. And again, we can say a rate of 0. That would be transforming it to probability 0.5. And then we can say, well, what about, I don't know, a standard deviation of 3. And we can see, right, it discounts extreme values. It looks good. And we know that by default, everything will be retransformed into a scale of 0 and 1s. And if we not smart, well, if we try to be smart and don't check, we think we have it all in our head, right? We'll not notice that actually when you put it on the scale between 0 and 1, you're going to have an extreme version of these. Because basically everything below minus 3 and everything above plus 3 is more or less equal to 0 and 1. 0.999, blah, 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 right? Which means that these part, even if it seems to have a lower probability, will compound with each other. and again go up here. In other cases, I think in the statistical rethinking model, it does the example of predicting height in some population, the Himba, I think. And then it says, well, we can have a prior for the standard deviation, a prior for the mean. Then we generate predictions, and suddenly we realize that there's quite likely to have somebody who's 5 meters tall. And that's even before looking at the data, given what we know about the word is silly. So that's where there's sometimes mathematical, sometimes common sense constraints that help us constraining the space of parameters that the model has to try out so that it's computationally more effective and it's less likely to give stupid results because we know something about the word. Another thing, I didn't really mention it, but when we were looking at those plots of tau, I'm actually going to go back. You can see between 10 and 15, the shape is very similar. If we did 20, 30, 40, 50, and we don't crash the computer, sometimes that happens, the plot is going to be exactly the same. So again, the model trying to fit the data would perhaps go that way and say, ooh, 15 is the same as 20. Maybe I should try to go further, right? And it would get lost in this region of parameter values that are indistinguishable from each other from a mathematical perspective, which means that the model would just waste time and that probably issues in finding its way there, getting trapped there. And the prior helps us getting away from there. We also have, I also put in the Prep Your Brain content unit, there is a link to very condensed version of Methods 4 tutorial that I did with Chris Cox, who's currently a postdoc with me and at the IMC, where we go through a few empirical examples on using priors. Generally, in this course, what we will do is we will do what they're called weakly informative priors. So priors that are just trying to put some common sense into the model, as I was just showing. It's often in empirical research, we might also want to say, oh, there is a meta-analysis that says that people with depression have a learning rate between 0.5 and 0.7, while people without a depression, or the same persons when they're not in a depressive episode, they have between 0.3 and 0.5, right? That's useful information. So what we could do is we could put a prior that respects, or a set of priors that respect the meta-analysis, and then very critically do the model quality checks that I'm saying, because that might tell us something more about our data than otherwise. For instance, now I'm going to change completely example, because that's the example in the video lecture that I put there. I was working on infant-directed speech in Danish, how parents speak to their children, in particular the acoustic measures. And in 90% of the published studies that are mostly in American English, we see that when parents speak to their children, they hyperarticulate. They open their mouth more, and the acoustic properties of vowels are bigger than when speaking to adults, right? Which is supposed to be for learning, right? So we do a meta-analysis across 1 million languages, and we say, okay, so so if this is 0, there is a tendency to hyperarticulate that we find in the meta-analysis, which is, I don't know, 0.6, right? And it's quite reliably above 0. It's a very solid result. We go and test a bunch of Danish mothers in that case, and we measure that, and it's a pain because you need to find the vowels and code them. And then what we find, if we just plot it, right, without this, is that Danish mothers are very confidently hypoarticulating, right? Just as normal Danes swallow all the consonants compared to Norwegians, right? Danish mothers tend to mumble more their vowels when speaking to their children compared to when they're speaking to adults or to their dogs, right? Then what we can do is we can use these as a prior and see what happens. And what we see is that, right, the posterior when using the meta-analytic prior is very different than when using a common sense prior, right? And we can do some critical reflection and say, well, this tells us two things. First, that Danish might be heterogeneous to the previously published studies. Something different might be happening in Danish. Second, that if we really want to make a good case, this amount of participant is not going to cut it, right? We need to have enough participants to push away from the meta-analytic prior, right? And then we can make a very strong case. Does that make sense? So even if the prior is biased, and I use bias in a neutral sense, right? It has information in it, which pushes the results in certain directions. By doing this comparative analysis with a weakly informative and an informative priors, we can actually learn more about our data and what to do next. Being biased is not always bad, also because sometimes we will say, well, I was doing a study on Moebius patients in Denmark, and those are patients who are born with the main nerve that controls facial movements is impaired. So they are just a stock face, right? They cannot move their face. And we were working on adolescents, and there were 5, right? And that was it. So what we did is we ran the study no matter what, because these patients are very rare, but also it's kind of important to take them into account. And we then used a very biased skeptical prior that said, well, with this amount of patient, we cannot say shit, right? But here are the data. Maybe you can collect 5 in Sweden, or 10 in Sweden, they're bigger, 5 in Norway, right? And 2 in Estonia, and so on and so forth, and gradually build a database in which we can do something meaningful. So priors are not a way for the researcher to put results into their analysis, though it might happen, right? That's why we should always be careful. They're a way of constraining the inference to common sense or to assess how well the new results stack against old results. Does that make sense? Yes, we'll do a lot of that, and there's videos on that are there, and I also will push a few more. Good. So we want to create the data set to do the data fitting, right? This is all the old stuff. I'm just going to put it very quickly. 120 trials. We create the random agent noise function. We create an empty data set. And then for all the values that we think are meaningful in noise and all the values that we think are meaningful in rate, in each combination, we create a vector of 120 trials. Visualize it. We've seen it before. I'm not going to go through that. It's just sanity check that everything works. Always do sanity checks. And then we start modeling, right? What is STAN first? You know, so STAN is it's titled after Stanislaw Ulam, who was a mathematician. And I discovered, like, the first time I taught this course, that there was just a movie that had came out, Adventures of a Mathematician, because apparently he had a very adventurous life. And it's been on my to-watch list since, because when you have 2 kids, I've seen all the Vaiana that you want, and Tornerose, and all of those, and endless series of pointless cartoons, but I very rarely get to see grown-up movies. But it's supposed to be actually quite good. And Stanislaw Ulam was working in New Mexico at the Manhattan Project. Right? That is at the project that was trying to turn intuitions about the inner structure of atoms into atomic bombs. And he had innovations on all sorts of things, including Hamiltonian Monte Carlo, which was, well, not Hamiltonian Monte Carlo per se, but Monte Carlo processes were developed to be able to track how the neutrons that you spray around when you divide a nucleus of uranium spread in the other uranium repository and generate new neutrons by splitting other atoms, which is a very complex and non-deterministic. Well, it is deterministic, but it's very noisy and stochastic, and it has a lot of moving parts. So you need to have algorithms that can deal with solutions that are not analytical, and that's why they use this name as name for the program. It's a probabilistic programming language, which means that it's a programming language which is specifically designed to deal with distributions. Not like R and Python, who deal with variables of other kinds. This is specifically aimed at working with distributions. And it's designed to specifically write down probabilistic generative models, right? So formalized models of a mechanism that generate data according to distributions, implements state-of-the-art Hamiltonian Monte Carlo samplers, which is the reasons for which I use it compared to JAGS, which Josh prefers because he has learned it before Stan became popular. And I'm not going to go through a lot of the details, but here there's a YouTube video on the specific samplers that you can refer to if you want more, and then you can ask questions. But I want to give you an intuition, and that means that we can look here. What are we seeing here? Here is a posterior space. It's a very abstract idea where we have two parameters. Let's say, for the fun of it, we have, on the x-axis, learning rate, on the y-axis, inverse temperature, tau. And this is the true distribution that would generate the data that we have, right? The darker it is, the more probable that is, the more likely it is for that value to be generating the data in this specific trial. And it's shaped like a banana. What the Hamiltonian Monte Carlo does is, you go away, right? It starts at random. You can see it there. And it goes in a random direction. And you can see that. It says it wants to go that way. But the banana has a shape. So what it does is it starts going that direction. But as it goes that direction, imagine it's a gravity well, right? As it goes that direction, the darker parts attract it more. So as it goes down, it starts fastening, bigger steps. But then as it starts climbing the gravity well, it starts slowing down until it falls back in. Right? And so in that way, it follows the shape of the banana to a certain extent. How does it do that? Well, let's start. That specific combination of temperature and learning rate has a certain prior probability given the priors. We see how well it explains the data, which means it gets a likelihood value. We combine the two and we get a posterior probability of that value. Then we do a step in the random direction. And now we have a difference, right? So if we got to a region that's better, we have acquired velocity. If we go a region that's worse, we have decreased velocity. Then we look around. a bit like gradient descent, right? We calculate the gradient in all directions, and that's the part that takes forever on your computer because it needs to look around in all the directions. And then it takes the velocity it has and it adjusts it according to the gradient, right? So if I'm going this direction towards Cassandra, but Balazs is a really big attractor, right? Even if I wanted to do this step, my step goes a bit around towards Balazs, right? And then it keeps going that direction. After a certain amount of steps, which we'll get to in a second, it stops and it says, okay, now I found a new sample, right? A new meaningful place, new meaningful value, combination of values for the parameters. That's going to be one sample, one iteration in your posterior probability. Then, and you can see, right, these were the starting values, and this is the additional one. Right? Then from there, it does another random step. It tried really hard to go that direction, but the attractor there is really strong, right? So it keeps going there. And then I'm going to let it autoplay for a while. And I'm going to take a bit less delay. And you can see that as it samples that posterior space, you start getting a distribution of the two parameters. The more time, the more iterations you give to the model, the more detailed that distribution is going to be. Does it make sense? The basic idea. Now, there are a bunch of steps there. So for instance, how many steps should it have, right? How much should it deviate according to the attractor? And so on and so forth, which are a lot of parameters that the equation governing that specific path, called the Hamiltonian, because it's an equation that has been developed by physicists to describe movements of frictionless particles in space, has some parameters, which we have no idea what they are. So what Stan does very well is it uses what is called the worm-in, or in JAGS it would be called the burn-in, I think. But in JAGS, it would use the burn-in, if you've done it with Andreas, to find a good place to start. In Stan, what it does, it uses the warm-up to try out different step size. For instance, let's say that it starts with this big of a step size. And for the people of the Zoom who will watch this video, it's just my hand, right? And if I start here, I'll take the whole hand. I start here, and then I go that direction. I'm actually going to overshoot. And that's going to bring me to a place where if I was here, I was going down, meaning that my velocity should increase. But the jump brought me to a place where my posterior probability has decreased. So the expectations of the model of the Hamiltonian are broken, right? I was expecting to increase my posterior probability, but I made the jump and it has decreased. I broke the physics of the model. Therefore, that step size is a bad idea, right? When it happens a few times, right, it has a learning rate that will slowly decrease the step size. On the contrary, if I have a very nice space, which is just a circle, right, very big, and I do micro step sizes, I'm never going to move around, right? I'm always going to be in the same place. And instead, we'll also learn from that and increase the step size, right? All of these Stan does it for us, right? We can go and mess with it. It's generally a bad idea. But we'll see how we can give it hyper parameters on how to do this better. Yes. So we're going to use R in this course because I feel more comfortable, because it builds more naturally on your previous methods courses, but you could use any other language. You just integrate the language that you use with Stan. In this case, we define the generative model in R. We simulate and prep the data. And then we prepare it for inference in Stan. Whoops. Then we use R to call the Stan model on the data that we prepared using R. And then Stan outputs a bunch of posterior samples and other stuff, and we can use R to explore it. Some people are a bit nitty-picky and say, if you use PyMC, you use Python all the way through. If you use Julia, you write your generative model, and then you push a button, and it also does inference. And that might be true, but first, I've never seen it actually work. Not to point fingers, but there's people in the department who are strong Julia proponents, and whenever we sit and try to do these things, that's so exciting. It never works, right? You still need to redo the model. Second, I don't care, right? What I'm trying to teach you is the base workflow. You use Julia, you use PyMC, you use Turing, you use whatever you want. It's great, right? You learn how to think. You can use whatever programming language you want. So what happens when you use Stan? R calls the Stan program into memory. The Stan program is translated into C++. The C++ is compiled into an architecture-specific machine-readable language, meaning that it compiles to different program according, for instance, whether using Mac or Windows. Right? You cannot pass those files around. And then the compiled problem is run. The model is fitted. That is, the posterior space is sampled and explored. And often takes a while. The output, samples, and diagnostic is made available to R. How does a Stan model works? Well, it has a bunch of chunks. And for now, we're only going to be focusing on the key ones. Data, because Stan is a picky eater, you need to make very explicit which kind of data you're giving it to, what's their value ranges, and what's the type of data, right? Which saves you a lot of time in retrospect, because when you specify things right, whenever you feed wrong data, it's going to spit out an error instead of running with the wrong model. How many times have you run LMIR or BRMS model where you thought you had categorical conditions for the experiment, but actually got run as a 0 and 1, right? A million times, me. Then we have parameters. I hope you have a good idea of what parameters are by now, right? Bias, rate, theta, learning rate, tau. And then we have the model. So when we infer, this stuff is always very good at being in the wrong place. When we infer a rate for a random bias model, right? We have some data, which is a sequence of right and left choices, meaning 0 and ones and zeros, if we say right and left. And we have an underlying rate. Do it? Yes. Rate or theta or bias, which is connected to the sequence of outcomes through a binomial, or more specifically a Bernoulli. That is a binomial only on one trial at a time. Generally, as a convention, shaded blocks here are observed data. Unshaded blocks are inferred parameters or inferred variables. And then we have a certain amount of trials if we want to run the fully binomial. Right. So we would say in statistical notation that the choice of right is determined by a binomial distribution with a rate of theta and the n of trial of 1, or that the choice of right is determined by a Bernoulli distribution with a rate of theta. Exactly the same thing. We then need to put prior And for instance, we could put a uniform between 0 and 1. Right? In this case, that makes absolute sense. But, we can also put a beta distribution with, this is very confusing, with a parameter alpha of 1 and a parameter beta of 1, which means basically that you had run the game twice and you got both results, a right and a left, which basically means that the beta distribution is going to be exactly like the uniform distribution. Does that make sense? Stan doesn't care what we use. We could also put something else. They gave you a hint before. That's usually what we do when we run logistic regressions, right? We can put a normal distribution with a mean of 0 and a standard deviation of 1, and then pass it through the inverse logic. So turning it from a log-out space to a probability space. And what it does, this is 0.5, is it's going to give us something that's something like this, right? Where 0.5 is going to be more probable than the other values. And we might opinate whether that's a good idea or not. Probably it's a bad idea, right? But it's perfectly possible to use that kind of things. And we'll see that when we go multi-level, working on log odds is very smart. So this is the Stan model, right? Before I represented it logically because it's very good to have a clear idea of what you're going to code. As I mentioned before, if you decide to use one of the large language models to help you, it's actually a very good idea to have all that conceptual structure very well specified in advance. So in the data, we need to put something, right? And we have the number of trials, how many data points it should expect, and the sequence of right and left. So what we can do is we can say data, curly brackets. There is one number that's an integer, which is n. We call it n. It could be anything, right? It could be trials. And then we specify lower equal 1. Why are we saying lower equal 1? Imagine that we have something that's lower than that. We have 0 trials. We want the model to spit out an error, right? And so sometimes you're running things automatically, right? You're parsing a bunch of logs and one log is corrupted or somebody didn't run, right? Just enter the experiment and then never did anything. If you have a script that reads how many trials there are and feeds it to the Stan script, it will spit out an error saying n expects lower equal 1, but n is equal 0, which is very interpretable, right? Then we have H, which is a sequence of right and left. We could call it anything. And then we have a bunch of stuff. First, we say that it's an integer. It can only be 0, 1, 2, 3, 4, 5, whatever. Technically, that's not enough, right? We could put more specific boundaries. And then we can say that it's an array of length n. Right? An array, in this case, since we only give it one dimension, it's a vector. Are you familiar with arrays and vectors? That should be methods 2 stuff, right? But basically, it's a sequence of number in one dimension. If we had n comma subjects, we could have a matrix where each column is a different subject and each row is a different trial. Right? If we had array n comma subject comma population, we could have a 3-dimensional array where we have 2 arrays overlaid in three-dimensional 3 space, one for one population, one for another. But we'll do a lot of these, right? So I'm just giving you the space of possibilities. If we want to put parameters, what should we put? Yes? Oh, sorry, theta, yes. Right, rate or theta. Parameters, we say that there's something called theta. It's not an integer, right? We don't want to have a rate that's either 0 or 1. We want a rate that can take any value between 0 and 1. So we say it's a real number which has a lower possible value 0 and higher possible value 1. And again, we could not write that and it would still work. But if we write that and something happens, it will spit out an error. We want our models to fail easily and eloquently, right? Then the last thing, and I promise we'll go through this again next week, so don't worry, or even tomorrow. So for the model, we have a binomial given theta and an n of 1, or a Bernoulli, right? So here we have, this is a bit more complicated. And I apologize for that, but it makes sense. It didn't used to be like that. A couple of years ago, we would have that H, our outcome was Bernoulli given theta, which made a lot of sense. Now we want to specify it as there is a log probability mass function given a certain sequence of ones and zeros called H and the rate of theta. Tell me how likely different values for theta are. Then given that we're Bayesian, we also need to create a prior. And here we have that there is a beta log probability density function, and I'll get to there in a second, where you have the values of theta that are generated here should be evaluated according to a beta distribution with an alpha of 1 and a beta of 1, a uniform distribution, basically. And I'm not sure how much of a closing of a lecture that is, but why are we using target? Target is super annoying, but it's making the inner working of Stan more explicit. Because if we write theta is distributed as a beta with an alpha of 1 and a beta of 1, we sort of have the internal image that we sample the full distribution. Well, it's actually flatter, right? And then separately, we go here and we say H is distributed according to a Bernoulli, given some value of theta. We sample the likelihood, right? Given the sequence of right and left that we have, what's the likely distribution of theta? And then we put those two together. And that's not how Stan works, because it would be completely intractable when the number of parameters increases. So what Stan does is at any given step, it says I have a theta of 0.5, right? How likely it is given the prior. Plus how likely it is given the sequence of right and left. This is my log posterior probability. I'm summing the two together. Why am I summing them? When Bayes' theorem is a multiplication, like prior times likelihood divided the evil stuff. Yes? Yes, because if we multiply small probabilities, 0.001 times 0.0001, we end up bumping into the how many decimals can a computer represent. So it's a bad idea to work in multiplication when you're using probabilities. If you remember from your high school algebra, right? If we turn things into a log scale, a multiplication is a plus, an addition, which means that we can work with arbitrarily small probabilities and sum them up without bumping against the limit of the computer. And the target plus equal is making very explicit that at any given sample, it's calculating its log posterior probability given all the target plus that there are in the model. We'll cover these again. I'm giving you the intro, right? So, are there questions on this? Technically, right, this is your very first STAN model. It takes some data. It knows the length of the data. It knows which kind of data they are. It knows that we want to estimate theta. It knows that we have a prior on theta and that the relation between theta and the data is given a Bernoulli. And then it does the magic for us, exploring the banana space. Right. Are there questions? Cool. The very last thing that I want to know is tomorrow we have 2 hours of class. Are you ready to submit the assignment 1? And then we start doing STAN of the models. And we can talk about that and take it more communal than last week. Good. That's what we're going to do, even if it's 8 in the morning. Yes, great. Thank you for today. Oh, yes. My email. Yes, I'm that kind of old fart. Yes.